Hey guys, welcome back to the channel. In this video, we will understand what happens during the ionization of polyprotic acids. Okay, so let's start with the video. First of all, it is necessary for us to understand what is a monoprotic acid. So the basic definition tells us that a monoprotic acid is an acid which produces one H plus ion on dissociation of one molecule. Now what is the meaning of this? Let's say you took one molecule of monoprotic acid, and if you took one molecule of monoprotic acid and after dissociation it will give you one H plus ion. For example, if you took one molecule of HCl, now this HCl after dissociation, one molecule of HCl after dissociation will give you one H plus ion. Therefore it is a monoprotic acid. The other similar examples are of your HNO3, nitric acid. It also gives you one H plus ion after dissociation. And one more example is of CH3COOH, your acetic acid. It also gives you one H plus ion after dissociation into ions. So I hope guys that understanding monoprotic acids was quite easy. Now let's move on to understanding what are diprotic acids. So here the process is little bit different but quite easy. Okay, first of all, the basic definition of diprotic acids tells us that the acid which produces two H plus ions on dissociation of one molecule. So it means that if you took one molecule of an diprotic acid and after dissociation it is going to give you two H plus ions. Okay, for example, H2SO4, sulfuric acid, H2C2O4, oxalic acid, H2S, hydrogen sulfide. So if you dissociate these molecules, it will give you two H plus ions. But it will not give you two H plus ions directly. Instead, the dissociation takes place in two stages. The first stage is primary dissociation and the second stage is secondary dissociation. Okay, so we will understand what is primary dissociation and secondary dissociation with the help of a H2SO4 molecule. Okay, so let's say that you have taken one molecule of H2SO4. Now in primary dissociation, what is going to happen is that this one molecule of H2SO4 will give you one H plus ion. It will give you one H plus ion plus HSO4 minus ion. So we are expecting two H plus ions, but we have got one H plus ion up till now. Now further on, what is going to happen? This HSO4 minus ion that we have got is going to undergo dissociation. Will undergo dissociation, secondary dissociation, and it will give us H plus ion plus SO4 2 minus ion. So guys, if you see over here, from this one molecule of H2SO4, we initially got one H plus ion, and from further on this another ion, that is HSO4 minus ion, we got one more H plus ion. Now if I want to write the overall reaction, of primary dissociation and secondary dissociation, then what I have to do, I need to add both these reactions. And after adding these reactions, what I get is H2SO4 giving us 2 H plus ions plus SO4 2 minus ion. So now in this overall reaction, you can clearly see that with the help of one molecule of H2SO4, you are getting 2 H plus ions. And since it is giving you 2 H plus ions, therefore it is obviously a diprotic acid. Now moving on to the next one, that is the triprotic acid. Now here the definition says that the acids which produce 3 H plus ions on dissociation of one molecule are called as triprotic acids. Suppose if you took one molecule of triprotic acid and if it undergoes dissociation, then it will give you 3 H plus ions. Okay, for example, H3PO4, phosphoric acid, H3ASO4, arsenic acid, H3PO3, phosphorus acid. Okay, now here the dissociation again is going to take place in 3 stages. Now for triprotic acids we want 3H plus ions, so we are not going to get 3H plus ions directly. Instead we are going to get them in 3 stages. Obviously your first stage will be primary dissociation, the second stage is secondary dissociation, and the third one is tertiary dissociation. Now let's understand them individually, and let us consider an example of one molecule of H3PO4, that is your phosphoric acid. Okay, so what happens during the primary dissociation is that we took one molecule of H3PO4. Now this one molecule of H3PO4 will get dissociated and will give us 1H plus ion plus H2PO4 minus ion. So from this H3PO4 molecule we have got 1H plus ion up till now. Now further on, what is going to happen? This H2PO4 minus ion will get dissociated further on during the secondary dissociation stage, and it will give us H plus ion plus HPO4 2 minus ion. Now can I say that up till now we have got 2 H plus ions. Now further on, what is going to happen over here? This HPO4 2 minus ion is going to further on dissociate during the process of tertiary dissociation stage, and it will give us HPO4 2 minus, giving us H plus PO4 3 minus ion. Now if I want to find out the overall reaction over here, then it is obvious that I need to add all 3 stage reactions, and after adding them, what I get is the overall reaction clearly mentioning that one molecule of H3PO4 after dissociation will give you 3H plus ions, and since it is giving you 3H plus ions, then it is obvious that it is a triprotic acid. So guys, I hope you have understood up till now what is monoprotic, diprotic and triprotic acid. But in this video our motive was to understand the ionization of polyprotic acids. So what is a polyprotic acid? That is the question. Okay, so let's understand this. So a polyprotic acid is nothing but the acid which produces more than 1 H plus ions on dissociation of one molecule. So any acid which gives you more than 1 H plus ions after dissociation of one molecule is your polyprotic acid. So guys, can I say that your diprotic acid was giving you 2H plus ions, whereas your triprotic acid was giving you 3H plus ions, which is more than 1H plus ions. So it is obvious that your diprotic acids and triprotic acids are also your polyprotic acids. Okay, now moving on. The acids ionize in stages which we have seen just now, but each stage is characteristic of appropriate ionization constant. Now what is the meaning of this? The ionization constant of each stage is going to vary. Let's see what is the meaning of this in brief. Okay, so guys, let's say that I have a acid H3A. Okay, so I have taken a triprotic acid H3A. Now what is going to happen in the primary stage? Okay, so primary dissociation stage, what is going to happen? This H3A will get dissociated into H plus ion plus H2A minus ion. So I have taken any acid, let's say H3A, it will obviously give you 1 H plus ion plus H2A minus. Now suppose if I want to find out the acid dissociation constant for this reaction. Now for those who do not know what is an acid dissociation constant, don't worry guys, I have already uploaded a separate video on this acid dissociation constant. You can find a link of that video in the description box below, or you can simply click on this I button which is there on the right top corner of your screen. This is similar to the equilibrium constant only. Okay, now suppose if I want to find out the acid dissociation constant. So what is the formula for acid dissociation constant? you just have to take the product of molar concentrations of products. So here the products are H plus and H2A minus. So I will take molar concentration of H plus over here into molar concentration of H2A minus divided by the molar concentration of H3A. Okay, so the square brackets indicate molar concentration. So I have taken molar concentration of products in the numerator and multiplied them, and I have taken molar concentration of reactant H3A and I have substituted it in the denominator. Now, further on, after the primary dissociation stage comes our secondary dissociation stage. So what is going to happen during the secondary dissociation stage is that this H2A minus ion is going to get further on dissociate and will give us one H plus ion, one more H plus ion plus Ha2 minus ion. Now if I want to again find out the acid dissociation constant of this reaction, then the formula is very simple. You just have to take the molar concentration of H plus ion, multiply it with the molar concentration of Ha2 minus ion and divide it by the molar concentration of reactants, that is H2A minus. Now we have completed the primary dissociation stage, we have completed the secondary dissociation stage. But since it is a triprotic acid, therefore we require one more stage, that is the tertiary dissociation stage. Now during this, what happens, this Ha2 minus ion will get dissociated into H plus ion, plus it will give you A3 minus ion. Now if I want to find out the acid dissociation constant, it is very easy. Just have to take the molar concentration of H plus ions, multiply it with the molar concentration of A3 minus ions and divide with the molar concentration of the reactant, that is Ha2 minus ion. So we have got the acid dissociation constants for three different reactions and I have named them as Ka1, Ka2 and Ka3, so that it is easy for us to distinguish. Okay, now if I want to find out the total reaction, so what I will do, I will just add all these three reactions. Okay, so the overall reaction now becomes H3A. It is giving you 3 H plus ions. Why it is giving 3 H plus ions? Because it is a triprotic acid. So it is a triprotic acid, will give you 3 H plus ions plus A3 minus. So this is nothing but the net reaction of all three reactions. You have just added 3 reactions and what you get is this reaction. Now if I want to find out the acid dissociation constant, let's say Ka, it is nothing but equals to the molar concentration of H plus ions. Now if you observe over here, this molar concentration of H plus ions is raised to 3. This 3 is nothing but a stoichiometric coefficient. So while writing the acid dissociation constant, you need to take care that if there is stoichiometric coefficient present, then you need to consider it as a power, raised to power. Okay, so molar concentration of H plus ions raised to the stoichiometric coefficient 3. Now if I don't know what is stoichiometric coefficient, I have already made a different video on that also. You can find the link of the video in the description box below, or you can again click on this I button. Now, so molar concentration of H plus ions raised to the stoichiometric coefficient 3 into molar concentration of A3 minus ions divided by the molar concentration of the reactant, that is H3A. Now, can I say guys that I have got the acid dissociation constant of the 3 stages, as well as I have got the acid dissociation constant of the final reaction as well. Now further on, what I am going to do is that let us multiply the acid dissociation constants of 3 stages. So let's say you multiply Ka1 into Ka2 into Ka3. Now after multiplying them, what you notice is that guys, the multiplication is equals to Ka, that is the acid dissociation constant of the final net reaction. Just observe this for a minute. See, observe this. This is same to this one only. Can you see over here? So if you multiply the acid dissociation constants of 3 stages for a triprotic acid, then you will get the acid dissociation constant of the final reaction. Okay, so this was easy, right? So it was a quite interesting thing that we observed. Ka1 into Ka2 into Ka3 will obviously give you the acid dissociation constant of the final net reaction. Okay, now this was one thing that you need to keep in mind. Suppose if I had a diprotic acid. So if I had a diprotic acid, then you need to answer below in the comment section that how many stages involved will be there, and you need to answer that how many acid dissociation constants do we need to multiply. This answer you need to answer in the comment section below, and I'll reply to your answer as well. Now, moving on. Let's consider this reaction, this slide again. Now, what I want you all to observe is that whenever you are writing the acid dissociation constant of the stages or for any reaction, in the numerator you are always having the molar concentrations of the products. Can you see over here? In the numerator you are having molar concentration of products. H plus is a product over here, and H2A minus is also a product over here. Similarly here, H plus is a product over here, and HA2 minus is also a product over here. Similarly, in the numerator of this acid dissociation constant Ka3, we are having the molar concentration of H plus, which is acting as a product over here, and A3 minus, which is also acting as a product. So just keep this thing in mind that in the numerator we are going to have molar concentration of products. Now, to understand further, we will move on to my book. So now let me first of all tell you what I have written over here. I have just shown that the molar concentrations are of product, then here in the denominator the molar concentration of reactants for all the 3 constants, and I have written the respective equations over here. So for this is the primary dissociation equation, this is the secondary, and this is the tertiary one. Now this acid which is there in the primary dissociation equation is also called as a primary acid. Okay, this acid which is present in the secondary dissociation equation is called as the secondary acid, whereas this acid which is present in the tertiary dissociation equation is called as the tertiary acid. Okay, now for almost all polyprotic acids, whether it be a diprotic acid or whether it be a triprotic acid, what we observe is that Ka1 is much more greater than Ka2, and Ka2 is much more greater than Ka3. So the value of Ka1, this Ka1 is much more greater than the value of this Ka2, and this value of this Ka2 is much more greater than the value of this Ka3. Now you might be wondering that why is it so. So let's understand this. See, why is the value of Ka1 greater? First we will understand that. Suppose if I want to find if I want the value of Ka1 to be greater, if I want this value to be greater, then the first thing that I need to do is that I need to increase the numerator. Am I right? If my numerator increases, then the value of Ka1 is ultimately going to increase. And the second thing that I can do is that decrease the denominator. So if I increase the numerator and if I decrease the denominator, then it is obvious that my value of Ka1 is going to be high. Okay, now how I can increase the denominator? If I am increasing the denominator, can I say, guys, that I am increasing the molar concentration of products? And if I am decreasing the denominator, can I say I am decreasing the molar concentration of reactants? Now, if I want to increase the products and decrease the reactants, so when it is possible? It is possible only in the forward reaction, where the reactants turn into products. And when reactants turn into products, it is obvious that the reactants will decrease and your products are going to increase. So here, during the primary dissociation reaction, the forward reaction is dominating. Okay, the extent of the forward reaction is greater. That is the reason that we are getting more products and less reactants, and therefore the value of Ka1 is greater as compared to Ka2 and Ka3. Now let me tell you all that why the value of Ka3 is less. We will understand that, but let me tell you all one thing, that can I say if this H3A is getting converted into H plus and H2A minus, then can I say that the H plus ions released is also increasing? Okay, so keep this thing in mind. For Ka1, that is the primary dissociation reaction, the H plus ions is increasing, the concentration of H plus ions is increasing, which means that the H plus ions are easily converted from H3A to H plus and H2A minus. Now let us understand why this Ka3 value is less. Now the one reason might be that the Ka3 value is less because its numerator is less and its denominator is greater. Now when can this numerator be less? When the molar concentration of these products is less. That means the H plus ions and A3 minus ions created is less. And when can this denominator be greater? When the reactants, the molar concentration of reactants is greater. Now when can you have reactants greater and products less? When is this possible? This is only possible when the reverse reaction is dominating. The reverse reaction is dominating, where the products are turning back into reactants. And when the products, this H plus and A3 minus, turn back into reactants, at that time what happens is that your products are decreasing and at the same time your reactants are increasing. So that's what you want. You want to increase the reactants and decrease the products. Now one question in front of you: why is reversible reaction dominating over here? Because can you see over here, there is a charge of 2 minus, and basically the job of this acid is to give away H plus ion, and since it is already negatively charged, the charge on this acid is already negative and it further on cannot give H plus ion easily, and therefore the H plus ion given out is less, and hence the reverse reaction dominates over here. So the extent of the reaction is less, the reverse reaction is dominating, therefore the value of Ka3 is less for the tertiary reaction. Okay, and here the charge is -1, therefore it can give H plus ion to some extent, therefore it is in between. It is surely not greater than Ka1, but it is at least greater than Ka3, because in the tertiary reaction the charge 2 minus is greater. Now this was one concept, that's okay. Now you need to understand one more thing. See, this primary acid is easily getting converted into its ion, and as we all know that acid which gets easily converted into its ion is nothing but called as a strong acid, whereas the acid which does not easily get converted into H plus and A3 minus ions is called as the weak acid. So here the primary acid is going to be the strong acid for most of the cases, and the tertiary acid is going to be the weakest acid, and this is obviously in the intermediate stage. Okay, now it is not strong nor weak, it is in between. So this was one more thing that you have understood. Now the another concept that you need to keep in mind is of degree of dissociation, which is represented by alpha. Now for those who do not know what is degree of dissociation, I've already made a separate video on this. You can find a link of the video in the description box below, or you can simply click on this I button which is there in the right top corner of the screen. Now for the degree of dissociation, what is degree of dissociation? In simple words, it tells us out of one mole how much amount of mole gets dissociated. Okay, so if you take 1 mole of primary acid, 1 mole of secondary acid and 1 mole of tertiary acid, who will get more dissociated? It is obvious that your primary acid, out of 1 mole of primary acid, almost 1 mole will get dissociated into ions. So therefore the degree of dissociation for the primary acid will be greater than the degree of dissociation of secondary acid, and the degree of dissociation of secondary acid will be greater than the degree of dissociation for the tertiary acid in most of the cases. Okay, so this was all about your ionization of polytropic acids, and that all you need to know for the examinations related to the ionization of polytropic acids. So guys, do check out my channel where I have uploaded physics and chemistry class 11th and 12th videos. They might be helpful for you all. And guys, thank you for watching this video.